So these are the parametric equations from graphs. So property for parametric equations for an ellipse. The general parametric equations for an ellipse are x is equal to h plus a cosine t, y is equal to k plus b sine t, where a and b are called the x and y radii, are in the proper ellipse form. This is the location of the center. For A and B are what we call the vertices and the co-vertices of the ellipse. And in this case, this is called the x radius and the y radius. And h and k are the location of the coordinates of the center. If A is equal to B, the figure is a circle, much likely. Okay, note that the coefficients A and B are also the horizontal and vertical dilations of the unit circle. X is equal to cosine t and y is equal to sine t. So it means that, it's the stretch of the y coordinate or the x coordinate. Okay? So if x is, for example, 2 cosine t, meaning that it was dilated by a factor of 2. Also, the constants h and k are the horizontal and vertical translations of the center of the unit circle. Okay? So let's do some examples here. For example 4, figure 4.5D shows the outlines of a cylinder. Duplicate this figure on your grapher by finding parametric equations of ellipses to represent the bases and then drawing lines to represent the walls. Okay, so the walls are actually the intervals of this ellipse. Okay, so meaning now we have 2 ellipses here, the one that can't be seen and the solid lines. So let's start with the first parametric function, first set of parametric equations, and that would involve the far right ellipse. This is the set, for example, let's call it set A, okay, of the parametric equation. So let's call it A of t, which is equal to the parametric functions or parametric equations x of t, and x is located at h axis. So that's located from 11. Okay, so h is located at 11 plus what is the dilation factor of the ellipse at the x-axis? That would be approximately 1.3. So that's 1.3 cosine of t, and y of t is equal to the location from the origin going to y would be at the center. We have 1, 2, 3, 4, 5, plus it is stretched by a factor of 4, 1, 2, 3, 4. So 4 sine t. Okay, we're done with A. Let's go to the other ellipse here, the solid line here. Okay, actually there's only one ellipse here, but you cannot see the other interval. So the other interval is dashed. So B of t is just half an ellipse. And B of t is equal to, let's call it x1, y1, this is x2, t, and x2t is equal to, where is it located? Where is the center located here? This is located at x is equal to 2. So that's 2 plus, still the cylinder has 2 bases, and this bases should have equal radii. So the radius here would be 1.3 also. And that's also the dilation factor. So 1.3 cosine t. While for the sine t, now take note that in our x we have an interval here. So appearing from, let's say, in between in between from 90 degrees, okay, going to 270 degrees, okay? So that's from 90 to 270, right? From here, from 90 degrees up to 270 degrees. So t is actually from 90 to 270 degrees, okay? While the y version, y to t, is not affected. It's still from 5 and 4 sine t. Okay, let's go to C, the dashed line. So this is C. C of t is equal to, let's call it x through t. And x sub 3t occurs, the center is still located at 2. And it has the same radius, which is 1.3 cosine t, and this time it goes from 270 going to 90. Okay, so it's from less than 90 and greater than 270. So less than 90. So t is greater than or equal to 90 degrees, but less than 270. I think it's actually greater than. It's actually less than 90 degrees and greater than 270 degrees, because 270 degrees is from here going to here to complete a revolution. Okay, while y3t has no restriction, it's still 5 plus 4 sine t. So these are the equations of the ellipses found in this example. Okay, so let's now go to certain problems. For problems 3 to 6, A, plot a graph in your grapher, sketch the results. Letter B, use the Pythagorean property for cosine and sine to eliminate the parameter t. And letter C, explain how you know that the graph is an ellipse or a circle. So let's go for number 3. Number 3, I think we don't need this one. So let's just erase this box. Okay, so let's not plot first the graph. Let's do the Pythagorean properties. So let's get a Cartesian value for this parametric function. Okay, so x here is equal to 3 cosine t, meaning that cosine t is equal to x over 3, and sine t is equal to y over 5. Now, following the Pythagorean rule for sine and cosine, to define a unit circle, we have cosine square of t plus sine square of t is equal to 1, providing as a model for cosine t is x over 3 square plus y over 5 square is equal to 1. Now this is an ellipse. Because an ellipse has different vertices and co-vertices. It has a stretch part on semi-minor axis. I mean, it has a longer stretch form on the semi-major axis, and a shorter and narrower form on the semi-minor axis. So if this is an ellipse, our center occurs at 0, 0, or the origin. Our A is equal to 3, and our B is equal to 5. And the location of our semi-major axis would be on the y-axis. So we have done this. Now we go back to letter A. Okay. So let's graph this ellipse. We have a semi-major axis at the y-axis. So 1, 2, 3, 4, 5. 1, 1, 2, 3. I think it's narrower below. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. This is our x-axis. This is our y-axis. Okay, this is 5, negative 5, 5, negative 5. So where is the location of our center? Our center is located at the origin. And our semi-major axis is in the y-axis with vertices occurring at 0, 5 and 0, negative 5. And co-vertices at 0, 3 and 0, negative 3. Okay, so because we already have those portions, these elements, now we can draw the ellipse. So the ellipse must be okay, we could just manipulate this and perform some adjustments. Okay. And stretch this on the horizontal part. So now we have our ellipse. Okay, our ellipse occurs having the center and the origin and semi-major axis on the y-axis, semi-minor axis on the x-axis. Okay, because we have a greater value for b, and this is it, our ellipse. Let's do this number 6. X is equal to 4 plus 3 cosine t, and y is equal to negative 1 plus 6 sine t. So let's use the same method. Let's first have to convert them into Cartesian form, so that cosine t here will be equal to x minus 4 all over 3, and sine t will be equal to y plus 1 all over 6. And following the model for the circle, for a unit circle of the trigonometric function cosine squared of t plus sine squared of t, this is equal to 1 for a unit circle. Then following that, we will define x minus 4 over 3 square plus y plus 1 over 3 over 6 instead. Square is equal to 1. Now this is a clear example of an ellipse because they don't have the same factor. The factor here is 1/3 or 1/9 if we put the square here, so this is 1/36. So because this is an ellipse, let's have the properties of the ellipse. Okay, what are those properties? Beginning with the center. Our center lies at 4, -1. Okay? Our A is 3. Our B is 6. These are the locations of the vertices and co-vertices of the ellipse. So, following that, we can now draw a sketch of our ellipse. So the center is located at 4, -1. So that means it's here. So we have to draw or label at least 6 scales up and below, let's say 7 scales. So below 1, 2, 3, 4, 5, 6, 7. And here, a 5x5 window may prove okay, but we have to extend it to, let's say, 10. Or 9 is okay. 1, 2, 3, 4, 5, 6, 7, 8. Okay. This is of course our x-axis, and this is our y-axis. Let's label the scales. So this is 4, this is -1, this is 10, this is -10, this is 6, this is -6. So we first have to locate the center, which occurs at 4, -1. Where is 4, -1? 4, -1 is definitely here. Okay? And next, let's use what do you call this? A more striking color. So 4, -1, and the location of the semi-major axis is at x is equal to 4. Okay? And the semi-minor is at y is equal to -1. So because our semi-major axis occurs at x is equal to, or y is equal to -1 instead, then we will have to count 6 units up and 6 units down. 1, 2, 3, 4, 5, 6. It would be here for the first location of the coordinates for the vertex, and this is the location of the other coordinate. 1, 2, 3, 4, 5, 6. So here. Okay? And for the horizontal stretch, the dilations are 3. So 1, 2, 3. 1, 2, 3. So here. And now we've completed our ellipse. And we could now draw an ellipse. So maybe we could use green color. And let's adjust. Okay. And to the right, So this is our ellipse. Okay? And that is for number 6.